Alright, in problem number 4, we're given a square, and the vertices of that square are labeled A, B, C, E, and we're told that the distance from A to F is equal to twice the distance from F to E. So they say AF is equal to 2FE, alright? So they're referring here to the lengths. The length AF is equal to twice FE. So if we were to draw a little hash mark here across there, then the length of these two segments, now that I have AF divided into, should be the same as this length from F to E. Alright, and we're also given that CD is twice DE, so the length from CD is twice the length from DE. So again, I could make a little hash mark here. Pretend that divides CD into two equal pieces. All right. So then these two segments that I divided CD into should be the same as the length from D to E. Okay. And they're asking, what is the ratio of the area of the triangle BFD? So that's this triangle that's inscribed inside of this square here. So they're asking, what's the ratio of that triangle to the area of the square ABCE? Okay. So there's actually a couple of different approaches that are very commonly useful when you're approaching these middle school geometry problems that are on the math contests. One approach is to divide the figure up into congruent shapes. That's not actually, helpful in this case. But what I mean by congruent shapes is that you can see maybe this is a small triangle. You could draw another triangle in this corner that's congruent, and you maybe try to break the whole thing up into the little triangles or something. But actually, that's not that useful in this case. But it's useful in a lot of geometry problems you'll find on the middle school math contests. The other approach that I find helpful is to impose a grid on the figure. Okay, because we don't really know the lengths of any of these sides, but we could draw, just like graph paper, we could draw a grid on top of this. And conveniently, we could divide, since this side AE, we can divide into 3 equal parts, and this side from C to E can also be divided into 3 equal parts. We could impose a nice grid if we draw a line across here. I'm try to draw it reasonably straight, and across here. Okay, so now we've got this square divided into 3 parts here. If we divide it by 3 parts again here, actually I better start by down here. I won't meet up where I want to go. Okay, I'm trying to draw straight. I'm not doing very well, but close enough for you to get the idea. Okay, so now impose the grid on this, and each one of these squares, if I drew all of these lines parallel to each other, they would all these squares would be congruent in this grid. Okay, because this is 1/3, 1/3, 1/3 of the side of this side of the square, and this distance is 1/3, 1/3, 1/3 of this side of the square. Okay, so then all of these would be squares that are like 1/3 the size of the big square. Okay, so we've got congruent squares now in here. So it's kind of like graph paper. So that kind of helps us see what we're dealing with. So that would be my hint to you, is try imposing a grid on this figure and see if that helps you solve the problem. So I'm going to go ahead and give you the solution now. So we're trying to find the ratio of the area of the triangle to the area of the square. And so it's this interior triangle, this BFD triangle. So the area of the square, now we don't really know dimensions here, but we could pretend like each one of these is 1, is a length of 1. So if each one of those is a length of 1, then each one of these squares is 1 square unit. Okay? And so we've got a 3 by 3 square, the way we've got it divided up, so we could just say, okay, so if we're taking that to be our unit of measure, this, this 1/3 of the side of the square, then the square, so I'm going to say the area of the square equals 9. Okay, now and that's 9 of these square units. Okay, so we'll just take that as our unit of measure. Okay, so that's fine as long as we can find the area of this triangle using that same unit of measure. Okay, so let's see if we can do that. Now, finding the area of this triangle directly doesn't look like it's going to be very easy. But always make sure, this is probably another hint that you often, for dealing with these geometry problems, is that oftentimes you can find the area of the thing you're looking for by looking at the area outside of the thing you're looking for and subtracting that from the whole thing. And that's what's actually easiest in this case. So here we have a triangle. Let me just mark this triangle here. Oops, actually, I'm going to go to a highlighter. I wonder if I can get a smaller highlighter. Looks like that's about as small as I can get. So I'm going to mark this triangle here. Alright, I'm just trying to fill it in. Okay, so we have that triangle here. And actually, we have another triangle down here that is actually congruent to that triangle. Alright, I'll just fill that in. Okay. So, now we can find the area of that triangle because it's a right triangle, right? And we can, the base here would be 2 and the height would be 3, so we can use the 1/2 base times height. And so 1/2 of 2 times 3 would just be 3, right? So that area of that is 3. And the same way here, if we use this as the base, so we have a base of 2 and a height of 3. And 1/2 base times height, we again get 3 for the area of that triangle. And then we have another triangle down here. I can mark that one as well. Okay, so we have that triangle. Now this one is a 1 by 1, so 1/2 base times height is just going to be 1/2, right? You can also see here the area of the square is 1 square unit, so this divides that square into 2 pieces, so each piece has to be 1/2. Okay, so now we have the area of the outside of the triangle. So the area of the triangle, so let's see the area of triangle BFD is going to be the area of the square, which is 9, minus the area outside of the triangle. And if we add that up, we get 6.5. So I'm going to write it 6.5. Okay? And if I subtract that, I get 2.5. Alright, so that's the area of the triangle, given our unit of measure, which is, we divided it into a 3 by 3 square. Okay? So now we have the area of the square, we have the area of the triangle. we can actually find the ratio. So the area of square, I'm just going to draw that, over the area of the triangle is equal to, whoops, wait a minute. I'm supposed to find the ratio of the area of the triangle to the area of the square. Oops, I better do that, huh? Better do the right thing. So I'm going to actually say area of the triangle to the area of the square. That's what we're asked to find. Okay, so the area of the triangle, BFD, is 2.5, and the area of the square is 9. Now usually you express a ratio in terms of whole numbers. So I'm going to actually multiply this by 2 over 2. That's just, well, 2 over 2 is just 1, so we aren't changing the quantity here. We're just multiplying by 1. But that allows us to express this as a 5 over 18 instead of 2.5 over 9 is kind of a complex fraction. So 5 over 18 is a better answer. And many of you may have also seen ratios written like this, where you have 5, you put a little dot dot to 18. So that's also another way to write it, to write the ratio. Okay? So there we have it. We found the ratio. We didn't really have any units. You know, that's not 3 feet by 3 feet or, you know, or anything. But we can kind of impose our own unit system by breaking it up into a grid like this. All right? So there you go.